Okay, great. Let's start.
We'll just start. Okay. Hello, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great honor to introduce our prestigious speaker, Professor Harrison Zhou. Harry is a Henry Ford II Professor and Chair of the Department of Statistics and Data Science at Yale University. He has made fundamental contributions to many areas of statistics. In particular, his main research interests include asymptotic decision theory, large covariance matrices estimation, graphical models, Bayesian nonparametrics, statistical network analysis, and analysis of iterative algorithms. His research has been acknowledged with many prestigious awards, including the NSF Career Award, the Nutter Young Scholar Award from the American Statistical Association, the Tweedy Award, the IMS Medallion Lecture, and the IMS Fellow from the Institute of Mathematical Statistics. The title of his talk today is Global Convergence of EM. Without further ado, please join me in welcoming him.
Thank you, Zoran, for your very kind introduction. And also want to thank you and Ethan for the invitation. And it's truly a pleasure to be here. And I also want to use this opportunity to thank the organizing committee, Zoran at Northwestern, and Neil at ETH, and Junwei at Harvard, and Tor at Georgia Tech. And it's a very difficult time for us, a very, very difficult time, right, at this moment. And thank you so much for bringing us together to understand fundamental topics in data science. And from the trend of COVID-19 cases recently, and I'm scared, I'm worried, and it's so difficult. And there may be a third wave. And thank you for organizing this. And at least we have some time to enjoy doing research, think about research. Okay, my topic is part of recent developments of non-convex optimization in theoretical computer science, optimization, and statistics as well. So, and I'll start to discuss a recent work with Yihong Wu and my colleague, and on global convergence of EM for 2-component symmetric and Gaussian mixtures. There have been a lot of research to understand this model and the performance of EM. But I have to say, this model is useless, okay, for real world application. It's too simple. So we have to go beyond to think about more general latent variable models. So, and today I will also discuss, an EM for a general Gaussian mixture. And the idea is to bring the recent success of over-parameterized and neural net. So there have been amazing, really amazing success and to show a global convergence of over-parameterized neural net. And it's kind of surprising to us. But of course, and it's not necessarily to be true. And the generalization error of over-parameterized neural net would be doing a good job. And the generalization error could be horrible. And if the true underlying function is not well approximated by the neural tangent kernel, the neural tangent kernel is a tool to understand the global convergence. So what we are hoping is to find initialization smartly, and also to make the model sufficiently over-parameterized, so that we could attain a computational global convergence at the same time, and some statistical guarantee. That's the hope. And Yihong Wu was just tenured 1.5 months ago, and he was tenured to tenured associate professor and very, very smart guy. I'm hoping and next year around this time, he will be a full professor. An EM algorithm is an algorithm to approximate an MLE. If we have a parametric model with an unknown parameter theta, we need to estimate theta. If the model has a latent variable, the log likelihood could be highly non-convex. That means we may not be able to get the global maximum. An EM algorithm has been quite successful to approximate MLE. It's an iterative algorithm. EM algorithm was proposed around 45 years ago. Actually, historically, it was more than 45 years ago. An EM algorithm, again, is an iterative algorithm. And for each iteration, it has two steps. One is E step, the other one is M step. And that's why we call it EM. At the E step, we look at the complete log likelihood and then take a weighted average. And the weighted average is calculated by considering the conditional probability of the latent variable given the data, and also theta t. In the M step, and we maximize Q. This is an amazing property of the EM algorithm. The log likelihood would be always increasing. I think that's the reason of the success of the EM algorithm. And if you look at the citation of the EM algorithm, and it's definitely one of the most cited algorithms in both statistics and machine learning. And I believe last year I checked the citation of this paper. It was more than 50,000. And this year is more than 60,000. It's amazing. But it's not guaranteed an EM algorithm would deliver the global maximum. And it can be often trapped in the local maximum. And that motivates us to consider global convergence of EM and give a theoretical guarantee. So we start with this very simple model. It's a Gaussian mixture with two components. And one component is minus theta star, that's the center. And the other component has a center theta star, symmetric. And for each cluster, and we have weight and 1/2. This is a very simple model, but it's not trivial. And because it's not trivial enough so that we could really gain some insight to understand global convergence of EM. And of course, it's simple enough so that we could, we could do some analysis. Okay, if you look at theta star, and it's not really identifiable if you want to estimate theta star, but it's identifiable up to a global and same flip. And so, that's why, and we define such a loss function, and to look at the accuracy of any estimated theta hat. Under this loss function, and the best rate to estimate the truth is d of n to the power 1/4. And some of you may be confused and surprised. And how could I get a rate d of n to the power 1/4? And we have a beautiful and smooth and likelihood function. And classical and MLE theory, and MLE is maximum likelihood estimation theory. Okay, and it's not machine learning theory. I'm sorry. ML in statistics is maximum likelihood. And the classical theory would say we should get d of n to the power 1/4 rate, 1/2 rate, and that's so-called root n rate. And when theta star is equal to 0, and the facial information is degenerate, is equal to 0. And that's why, and the rate over here is inferior to the classical rate. By the way, in this talk, I will consider L2 norm of theta star is bounded. If it's not bounded, we have similar results. For this simple model, the EM update has a very nice form. It's very simple form. And the update is a weighted average of YI. YI is your data. And the weight is given by the tangent hyperbolic function evaluated at this point. So some of you may not remember tangent hyperbolic function. So I put the form over here in case you don't remember. So the tangent hyperbolic function arises naturally and from the conditional probability calculation of the latent variable. To understand the sample version, we have to understand the population version first. And this is the population version. And usually it's much easier to analyze the population version because everything over here is deterministic. And for the sample version, the analysis could be much more complicated than the population version. The reason is this: the output theta hat over here depends on your data. So the output and your data could be dependent. When they are dependent, then the analysis could be very hard, very challenging. For this simple model, and the EM update is identical to gradient descent with a linear rate constant 1. And this is a fun fact. It's fun fact to know. And for general Gaussian mixture, and you have similar phenomena, and it's also related to gradient descent, but with a different linear rate. And we were inspired by this paper. I guess the paper eventually appeared a few years later in the Annals of Statistics. The first author and was interviewed at Yale and 6 or 7 years ago. And his job talk was on EM, global convergence of EM. And for symmetric and two-component on Gaussian mixtures. And they show that if two centers are far away from each other, and the initializer, is very close to the truth, then they show the global convergence of EM. And 2 years later, and some scholars and Columbia showed a surprising result. They show that for the population version of EM, you will always get a global convergence as long as the initializer is not orthogonal. It's not orthogonal to the theta star. If it's orthogonal to theta star, you'll get trapped over there forever. Around the same time, theoretical computer scientists at MIT did a similar analysis. They also considered the sample version. And to, as I pointed out and on the previous slide, and for the sample analysis, it could be challenging because of the dependence of the output and the data. So they do sample splitting and also some other tricks to succeed. It's a very nice work. But we have to admit that's not what we do in practice, right? We will not do sample splitting. If you do sample splitting for every step, and the performance will be horrible of the output. Okay, so and these three papers motivated us to ask this question. The question is, can we have a faithful analysis of EM no sample splitting, no without a strong separation condition, and without warm initialization. Can we show global convergence of EM? And by the way, there are some other papers after this one, and but I'm not listing over here. I apologize. And if you do not see your paper, this is our first success. As a principle of doing research, we always start with the simplest case, d is equal to 1. And for one dipinner case, and we show that for any initializer, as long as it's not equal to 0, an EM converges after at most square of n iterations. Without separation condition, theta star could be equal to 0. Without, sample splitting. And we even show that, and the rate is optimal. When d is equal to 1, the rate is n to the power minus 1/4. That's the optimal rate. If it turns out theta star is bounded away from 0, and the rate is actually parametric rate, and the classical parametric rate. And the proof of this result is kind of trivial as well. And what we do is this: we approximate the sample version by the population version. The solid blue curve is the function of the population update. The intersection with the 45-degree line is theta star. That's the only fixed point. We sandwich the sample version by an upper overlap, or upper envelope and a lower envelope. For both upper and lower envelope, you see that there is only one fixed point. The upper envelope gives us an upper bound. The fixed point of the lower envelope gives us the lower bound. And the difference between the upper and the lower bounds and gives us the optimal rate over here. So for one dimensional case, the analysis is very easy. So what we really need is just to approximate the sample version by the population version. And the population version analysis is relatively easy. Then the second step is to consider d equal to 2. When d is more than equal to 2, and the output now has two components. One is the signal component, and the other one is orthogonal to the signal. And the orthogonal part is quite easy to analyze. And you could show that the orthogonal part would decrease to 0. But it's not equal to 0. Because it's not equal to 0, it may interfere the analysis for the signal component. That makes the problem hard. And there is another difficulty for higher dimensional case. For higher dimensional case, if we approximate the sample version by the population version, what you have over here is no longer 1 over square root of n. You have square root of d over square root of n. When d is close to n, the error over here could be too big to be controlled. By the way, due to the rotation invariance of Gaussian distribution, and you may just assume the first coordinate is not equal to 0, which is L2 norm of theta star, and the rest of coordinates are equal to 0. In terms of analysis, you may just assume in this way. So in this talk, you may just assume the most important part is the first coordinate, and you hope the alpha t would converge to L2 norm field stop. Then the rest of coordinates goes to 0. That's the analysis we need. So this is our main result in the paper with Yi-Hong Wu. If we pick an initializer randomly from a unit sphere, actually in our paper, we did not use unit sphere. We use a sphere with a small radius to make the paper shorter. Otherwise, the paper would have to be 20 pages longer. And we assume that, and the sample size is more than the dimension of the data, up to a log factor. Then the EM algorithm converges. And the rate over here is optimal, up to a log factor. After, at most, and square root of n and times log n steps. And it's very important to mention that one random initialization is enough. You do not need to do many initializations. And also, we do not need to do sample splitting. In addition, we do not need any separation condition. Field star could be equal to 0 or close to 0. You will always get the convergence of EM. If we have some separation condition and bigger than the estimation accuracy, we can show that the EM algorithm is not only rate optimal, but also attaining the right constant. By showing that EM algorithm indeed converges to MLE. You could even show that converges to MLE. Here's the proof. If you do not care about the proof, you may take a nap. Okay, again, and some of you may be from China. It's 11:30 p.m. or 11 p.m. So, so it's good. Yeah, and if you do not care about proof, just forget about it. And some of us care about the proof, including Zhou. Okay, the proof has 3 stages. The most difficult stage is stage 1. And if we pick a random initializer from the sphere, the random initializer would be nearly orthogonal to the truth. That's the first step, right? And then we hope after the stage 1, the angle would become less than 90 degrees, like 89 degrees. That's stage 1. That's what we hope to prove after stage 1. That's the most difficult proof. And after stage 1, and then we move to stage 2. In stage 2, the proof is kind of routine. It's very similar to the proof of one-dimensional case. Just approximate the sample version by the population version. And if you know the convergence of the population version, basically you know the convergence of the sample version. And if you have good control for the between the sample version and the population version. And after stage 2, then we could get a good rate of convergence. And then we move to stage 3. And stage 3 gives us not only the best rate and also the best constant. And if we have some signal. So before the pandemic, I gave a talk in Netherlands in honor of Otto van der Waard at Leiden University. I was using this, and I was using my traveling to Leiden University as a way to illustrate the proof. And we could fly to Leiden either from US or from China. Actually, I was from China. I was doing fundraising in China then. At the very beginning, okay, the angle was like between China or US and with Europe, it's like 90 degrees. Okay. And okay, the first flight is long, it's hard. After we arrive in Europe, I believe I fly to Germany, and it's rather easy to go from Germany to Amsterdam. After we arrive in Amsterdam, it's becoming easier to go from Amsterdam to Leiden University. And now during the pandemic, a lot of people are starting to do long distance routing, and we are bored at home. And you could even run from Amsterdam to Leiden if you like running. And then you would attain a symptotic efficiency there. So in the stage one, a key argument is this, is to show that the signal component and grows after each iteration. And for the orthogonal component, it's very easy to show it just decays to zero. That's very easy. But the proof is hard. It's hard because of the dependence of your output and the data. It's not easy to get the letter O of this term there. And we succeeded by learning from this brilliant paper and by Princeton scholars. They introduced a technique called sign perturbation. So we have our original data, yi, y1 to yn. Only the first coordinate has signal, the rest do not have signal. We perturb the first coordinate by multiplying the first coordinate by an independent random marker, -1 or 1 with half probability. Y tilde and Y now have the same distribution. If you run EM using the perturbed data, then the output theta tilde would have the same distribution as the output of the arranged data. So that means to analyze theta hat, you could just analyze theta tilde. A good thing about theta tilde is its first coordinate is independent of the sign theta tilde is independent of the sign of the first coordinate. That's a very good property of theta tilde. And we explored that property and to succeed. At a very high level, okay, if you run EM, right, you started with a random initializer, and the angle was like 90 degrees with the truth. You do not really have any signal there, right, at the very beginning. That means the output, yes, the output are dependent with the data, but nearly independent of the data. The question is, how do you explore that property in your analysis? It turns out, this trick did the job. Did the job to explore that intuition. So after the stage one, and the angle is now less than 90 degrees. Your output, if you look at the signal component of your output, the signal component of your output is right over here. It's no longer there. Okay, that was a mess. Okay, that was a mess. You do not want to be there. It's now over here. And since your signal component is over here, you see that if you're bound and the sample version by an upper envelope and an lower envelope, and you see there's only one fixed point. And after you have only one fixed point, and the analysis is becoming easy. It turns out, and for the signal component, and you could show that, and the upper bound and lower bound can be well controlled and by d over n to the power minus one quarter after a log factor. And equivalently, and we could show that and the EM output is very close to the true signal, and the rate over here is optimal after a log factor. That's stage 2. So stage 2 analysis again is nearly identical to the one-dimensional case, but of course it's slightly more complicated because D could be large. After stage 2, then we get a fairly good accuracy of the estimation. Then we try to get the right constant as well. To get the right constant, the analysis is very similar to the analysis of the celebrated paper by Peter Baker in 1975. And what he showed over there is this: if you have a good estimator, if you run one step Newton-Raphson of the likelihood, and then you get not only the right rate but also the right constant. Of course, we cannot run the Newton-Raphson. We have to run EM algorithm because we want to be faithful to EM algorithm. We want to prove EM algorithm is doing the right thing. And we show that. And if we run EM algorithm on many steps, and equivalently, it's like the estimator would be equivalently like MLE. And then you get the right rate and the right constant in a risk bound. And this is the proof. The proof is, okay, the t+1 step output is theta t hat plus, okay, gradient descent with learning rate 1 minus MLE. Okay, what's this term? Oh, this term is just 0, right, by definition. Then you do Taylor expansion. And if you could show the spectral norm of this matrix is bounded by 1 with high probability, then you're done. You get contraction to MLE. That's the proof. So after 3 stages, then we prove this theory. The first 2 stages and gives this result. The last stage and gives this result. So after we finish the work, and some of our friends really like it because the analysis is very delicate, and some inequalities and all the identities over there that could be useful. But some of our friends hate it because it's too delicate. You cannot really extend it to more general Gaussian mixture. So I'll be very sad if we have to stop over here, right? And so we hope to go beyond the covariant analysis and to more general and latent variable models. So and we use the overpolarization idea, and as many of us know that Simon Du and people in EPFL and have showed the global convergence of overpolarized and neural net, and by looking into basically the connection between overpolarized neural net and a neural tangent kernel if we run gradient descent. So this is joint work with G.E. Liu and a PhD student at Yale, and Anderson Zhang, a professor at Wharton, and he's very, very creative. So, okay, this is a general Gaussian mixture. We have n observations, and there are k centers. In the previous example, and k was equal to 2. There are k centers. And Z is assigning each observation to one of the centers, okay, or one of the clusters. Okay, we have k clusters. So, and we hope to estimate the Gaussian mixture, which is basically equivalent to say, to estimate, the label and the centers. And there is another very popular way to formulate a Gaussian mixture is to write Gaussian mixture as a convolution of Gaussian and the mixing distribution of the centers is a discrete distribution, and with k atoms, theta 1 to theta k. And for each atom, there is a weight. And the value of the weight gives us the size of the cluster. So learning Gaussian mixture is basically equivalent to learning a discrete distribution. The discrete distribution is the distribution of the centers. So, and this is our over-parameterized EM. So, okay, although there are only k centers, we start with M centers. M could be far bigger than K. The question now is this: how do you pick those M centers to start, right? You could do some kind of uniform sampling. And our way is this: we pick M data points from the sample. Okay, there's a reason for us to do that. Actually, this is very critical for us for the success of the algorithm. And we pick, M data points from the sample, so that around each true center, and you will see some data points. You will see some data points at the center of the initializer. And then, okay, when we run the EM update, right? And if for each iteration, and if we send in an M centers, and the output will be M centers. And in a sense, we start with IID sampling, M IID sample, and then the output will have identical distributions. The all output will have identical distribution, but they are not IID. Okay, they are not identical distribution, but not independent. A very good problem over here is this. A very good problem is if when M and N go to infinity, the output are nearly IID as well. So that is helpful for our analysis. So, okay, and a summary of this procedure. The summary of this procedure is this. Okay, we want to learn a discrete distribution, right? With k atoms and with a certain weight and for each atom. We want to learn a discrete distribution. And we start by picking the sample, a subsample. So the starting distribution of the centers would be just an empirical distribution of my sample, right? It could be far away, very far away from the discrete distribution we want to get. But what we're hoping is this: after many EM iterations, the distribution of the center would getting closer and closer to the true mixing distribution of the centers. So, okay, let me illustrate by this simple example. It's Gaussian mixture, okay, and with 3 centers. So, what we really want to learn this Gaussian mixture, what we really need to learn is to learn the discrete distribution with a weight 1/3 at minus 1.5, 0, and 1.5. That's the distribution we need to learn. If you know the mixing distribution of the centers, and then we are done, right? So, but we are starting, let's say you have 1,000 data points to start. And we are going to pick a subset of sample. And let's say 100 points as my centers. So the truth is 3 centers. but we start with 100 centers. If you look at those 100 centers, if you look at the distribution of those 100 centers, it will be very similar to this one, right? Because it's just a empirical distribution of this guy. It's very far away from the discrete distribution here. The discrete distribution with 1/3 weight at minus 1.5, 1/3 weight at 0, and another 1/3 weight at 1.5. It's very different from this discrete distribution. But what we're hoping is this, the EM algorithm will do the job. So okay, the sample size is 1,000. The truth is we have 3 centers. We want to learn the discrete distribution with 3 atoms and with weight 1/3 equal weight. After we pick 100 sample points, let's say 100 centers to start. So initially, if you look at the 100 centers, the distribution will be very much like this, okay? Because that's the empirical distribution of this guy. After 20 iterations, then you start to see 3 modes. After 200 iterations, the 3 modes are becoming narrow. After 1,000 iterations, then you really see just 3 point mass with weight 1/3 and for each point. That's the algorithm. And if you pick 200, if you start with 200 centers or even 1,000 centers, okay, the point is the center, and you get a similar result, very similar result. But the bad thing over here is this: it would take a longer time to converge. So I'm not sure if you understood the simulation. The simulation is we want to learn the discrete distribution with 1/3 weight at minus 1.50 and 1.5 equal weight. And we start with a distribution similar to this guy. Then after many iterations of EM, then eventually we get a distribution and very close to what we want. So, and we have some theory to prove a global convergence of the mixing distribution for some very simple cases. But we do not have a complete theory yet. And hopefully, and during this summer, after stepping down as chair, and I will have more time for research to get a complete theory. And so far, the theory is, I don't think they are good enough to be presented, to be reported over here. And I'm not even clear whether I would get the optimum rate convergence or even the optimal constant. If it's not, maybe we would have to look at some other alternatives to improve the current update. I hope we do not need to, but and at this moment we do not know. So okay, that's all I have to say. Thank you all.
Thank you, Harry, for the great introduction to the EM algorithm. So as for the questions, the first question is for these 2 settings, the 2-component Gaussian mixture and multiple Gaussian mixture with multiple components, do you have a lower bound result, especially for the first case that your result matches the minimax lower bound?
Oh, you mean for the general Gaussian mixture?
Yeah.
Yeah, for general Gaussian mixture, we have a paper which is under revision for the annals of statistics, and we have a general estimation result and under the Wasserstein distance. We have one, yeah, and that's a paper with my student Natalie Das and Yihong Wu and Peng Kun at Tsinghua University. And by the way, Natalie is now at 2 sigma, so this is sponsored by 2 sigma as well. So that's a good thing.
Yes. So, and also, is it easy to extend beyond the identity covariance matrix?
Oh yes, that's very good question. Yeah, and after each iteration, then gradually you will see cluster information, and then you could add and covariance estimation in each step as well. Mm-hmm. In terms of the algorithm, you can definitely do it. And what I do not know yet is the theoretical guarantee. And in terms of the algorithm, it's very easy, right? After each step, you can always, and you would at the same time you update the covariance. That's very good question. Very, very good question.
Thank you. And also for the second setting, the Gaussian mixture with multiple components, it seems there's a statistical computational trade-off when the number of components is large, and that is the minimax lower bound is there's a gap between minimax lower bound and the optimal performance achieved by polynomial time algorithm. And I was wondering, when you do this over parameterization, do you observe this computational statistical trade-off? And
actually, and in my paper with Natalie and Yihong and Penguin, we attain the upper rate under the Watson distance. It's very strange rate, okay, and even for k-log, it's very strange rate. And of course, and we are assuming k is finite, and when k is finite, and then the computational computational complexity over there is n to the power and 5/4. It's not too bad. N to the power 5/4, so it's not too bad. But when k grows, okay, and when say if k is bigger than log n, and we do not have any separation condition, in that case, and from the in that case, and then you'll see that, and the rate is and the best rate you could get is not consistent. So that means the components and we consider has to be less than log n.
Thank you.
I mean log n order. Yeah.
Yeah, and another question is from Yudong Chen from Cornell, and he has actually two questions. The first one is, when the Fisher information matrix is degenerate, how is efficiency defined, and is EM efficient in that sense?
Oh, and and so over here, and we talk about efficiency. When theta star is slightly moving away from the estimation accuracy, so we have some signals, and then we define efficiency and efficiency. So that's the reason we talk about statistical efficiency, because we have some signal over there, and otherwise the efficiency definition is very strange, and even for d equal to 1 case, if you look at even for d equal to 1 case, if you look at MLE, when theta star is far smaller than n to the power minus 1/4, then the distribution of MLE is half normal. Okay, it's not full normal, and when theta star is far bigger than n to the power minus 1/4, and then you get this classical MLE theory. When theta star is at an order of n to the power minus 1/4, and it's becoming complicated. It's a mixture of half normal and the classical normal. So and we try to avoid talking about that. So that's why we assume the signal is far bigger. And I mean, the signal is the separation is far bigger than d over n to the power minus 1/4. Yeah. I mean, n to the power 1/4. I'm sorry. Yeah. That was the first question. What's the second question? I forgot. from Yudong.
So in this sense, in the case where the facial information is degenerate, is EM still efficient in that sense?
And efficient and only efficient in this sense to obtain the right rate. That's the best I could say now. I do not believe the distribution would be matching the MLE distribution. I am skeptical. I don't think so.
And actually, Yudong has a second question is about spectral methods. And it is known that spectral methods also achieve 1/4 statistical rate in the order. So that is the D divided by N to the power of 1/4. And does the spectral algorithm have worse constant on, and how do you compare the spectral algorithm with EM empirically and theoretically?
Yeah, that's a very good question. I have never thought about it, and that's a very deep question. And I'm not sure. And my instinct is this, and for the spectral method, the constant is worse. And but I never got a chance to really analyze it. And when two centers are far away from each other, okay, it's easier to analyze the spectral method. But when two centers are close at a constant order, and the spectral method, or even smaller than that, and the analysis of spectral method is becoming very complicated. I do not know. That's a very good question.
Thank you. And so another question from Kaizhen. His question is for the multi-class Gaussian mixture model with over-parameterized EM. So that's a question about the second part. The question is, what is the key assumption on the initialization?
And so this is not a very good question, and that's why we pick the centers in this way. And we pick the centers, we pick centers in this way. Okay, if I pick centers in this way, in the one-dimensional case, okay, if you look at the distribution, right, of the centers, you will have a positive mass around the center. In the high-dimensional case, of course, you do not expect a positive mass right around the center and a very small neighborhood of the true center. But the good thing is this, and you may have a positive angle. And if we have a positive angle, if you look at the inner product and between if you look at inner product between the difference of any two centers, so we would like to explore that one to get the convergence.
Mm-hmm. Yeah. So the second part, I think you have maybe answered it. So the second part of this question is, does the theory require each true center to be close to some initial guess in your initialization? And this might be hard since in the high dimensions, all samples are far from the true centers. So the question is still about the initialization. So does the theory need the true centers to be close to some initial centers in your?
I'm sorry.
So is there a connection issue?
I think he is offline.
Yeah, he's here again.
I'm sorry. Yeah.
See, let's wait for a few seconds.
Yeah.
Can you hear me?
Yes.
I'm sorry, yeah, I lost you and the internet was bad. I apologize.
Yeah, so since now you are not sharing your screen, you can see the Q&A. It's on the
Oh, okay.
At the bottom.
So what was the question? I'm sorry, I apologize. Yeah, so Kaizen asked very good question is you know what do you mean, right? And when the height mean case, what do you mean? The centers to have each center you have some kind of initial gas to be close to it, and it's not guaranteed. But the good thing is this: the good thing is what you really need is not really what you really need is somewhat closer to one center to the other one.
Yeah. Thank you for answering these questions. I think these are all the questions we have so far, and so I guess we will just stop here. And thank you again for the great talk, and thank you for your time.
Oh, thank you all for having me. It's fun. I also enjoy very much the question from Yudong and Kaizen. They are true experts in the field.
Thank you, and also we would like to thank the audience for coming today, and look forward to seeing you next week.
Okay. Thank you all.
Thank you.